Hi students, welcome back. Coming to the next point, and the most important concept is the floating point representation. In the previous video, I explained about the fixed point representation where the binary number is fixed in fixed point representation. But whereas in the floating point representation, the binary point floats to the right of most significant one, and an exponent is also used. So we are representing the floating point in the scientific notation. So this is the meaning of the scientific notation. A number can be represented in scientific notation. How the binary number can be represented in scientific notation? That is the plus or minus m into b power e. So this is a representation of the scientific floating point number. So here whatever the binary number we are taking, that the binary point in that is floats to the right of the most significant one, and here we are using the exponent also. I'll explain how to represent also, but let me tell you the floating point representation is one of the important concept, and nowadays whatever the technologies that we are using, in the technologies, the number system we are following, that number system is represented in a floating point. That is a scientific notation, means in this format. If you observe the speed of the light and charge of electrons and the age of the universe, everything is represented in the form of this format only. Okay, so the mantissa, base and exponent format. The floating point representation has three parts: mantissa, base and exponent. Actually, the floating point numbers can be used to represent a very small as well as a very large numbers. It will be used for both. So that's why we are following the floating point representation rather than the fixed point. So it has, it can be used in very small numbers as well as a very large numbers also. And if you observe here, it has the three parts: the mantissa, base and exponent. So whatever the binary number that we are taking, that binary number is represented in this format. Okay, so remember, don't forget this format. It is mantissa, base and exponent. Here I have taken some examples for you how to represent a number, whether it is a decimal number or a binary number. So that number can be represented in, so this is a number 9 into 10 power 8. So this is already in the floating point representation. That is a scientific notation. So it is in the form of plus or minus m into b power e, where m is a mantissa. So here what is an m? 9 is an m. Okay, and what is the base? So the base is this. This is the powers. That is a base. So the base is 10. And what is an exponent? Exponent is 8. So this is a representation of the floating point number, scientific notation. Okay, in the form of plus or minus m into b power e. Suppose if you take this type of number, in this number, the mantissa is 110 and the base is 2 and exponent is 7. And if you take these type of decimal fractions, so these type of decimal fractions can also be represented in this format. So first of all, let me find out what is a mantissa here. The mantissa is a complete number. This is a mantissa. And what is a base? So the base, you can convert it into 10 is a base, and exponent is minus 3. Because I shifted the dot here. So whenever I move the dot, the decimal binary point, then you'll get the exponent 10 power minus 3. 4364784 into 10 power minus 3 is nothing but this value. Okay, nothing but this value. So here what you observe, the binary point, whatever the binary point is there, the binary point can be float. It is floating. It is floating to the rightmost significant one. And an exponent here we are using. Okay. So this is about the floating point representation. Now let me tell you about the IEEE 754 floating point number representation. The standard that we are following in the floating point, that is the scientific notations, whatever we are taking, it is having some standard, that is IEEE 754 standard. So these IEEE 754 floating point number representation can be represented by using single precision format as well as a double precision format. So what is a single precision and what is a double precision? Single precision means here we are taking the bit size as a 32 bit. we are considering a 32-bit can be represented in the form of a single precision format, and the double precision is 64-bit. So whenever the size of the register is a 64-bit means we have to represent it in a double precision format, and if the size of the registers is in 32-bit means we have to use a single precision format. So the single precision format, whatever the size of 32-bit is divided into, the complete number is represented in the form of sign, exponent and mantissa. So these mantissa and exponent can be interchanged. So sometimes we are writing here the exponent mantissa and here the exponent, and sometimes here exponent and mantissa. So don't get confused on that. So you just check with the numbers, the number of bits that are assigning for the exponent as well as the mantissa. So the mantissa, the number can be any number, infinity. It can be infinity. You can write. So based on the size, you can increase the number. Based on the size, you can increase the number. Even though you got only the 8-bit, you are going to represent in the 32-bit format means increase the numbers in the mantissa by adding the zeros or whatever the format that format has to be followed. Don't get confused. I'll explain that concept also, how to add the bits to make it as a 32-bit and to make it as a 64-bit. Okay, but here in this session, you just focus on how to represent the single precision formats and the double precision formats. So the 32-bit is divided into, the 1 bit is only for the sign bit, 31 and 30. It's a sign bit. The most significant bit always indicates a sign bit. If it is 0 means it is a positive number. If it is a 1 means it is a negative number. So the most significant bit is always a sign bit. That is 1 bit. Okay. That is 1 bit. And coming to the exponent. In a single precision format, the exponent is of 8 bits. Exponent size is 8 bits, and whereas the mantissa is 23 bits. So this is the representation of the single precision. Then what about the double precision? Same thing, but you need to do the double. The size of double precision format is a 64-bit, 0 to 64. So always take 0 to 63. 62 and 63, that is a sign bit, which is a 1 bit. And next is the exponent. You can write here exponent as well or mantissa, anything. Okay. And 62 to 52, and this is almost 11 bits. The 11 bits are used for the exponent, and the mantissa is 52 bits. 0 to 51 means 52 bits. So this is a format. It is a IEEE 754 floating point number representation. So in the next video, I'll explain how to represent the numbers in a single precision format and double precision format. Okay. Thank you.